Hello everyone and welcome back to another quickie on the Fundamental Theorem. In this video, we are going to look at why the number 0.9 with a bar, so that's nothing but 0.99999, etc., where I have infinitely many nines, is actually equal to 1 exactly. Right, so there are many ways to approach this, and one very simple approach is an algebraic approach, and you can look that up. I'm not going to talk about that now. You can just treat uh, all of the decimals in terms of, well, I'll leave that to you to figure out. I'm not going to talk about that now. What I'm instead going to do is approach this using the fundamental properties of the real numbers. And though this isn't going to be any rigorous real analysis per se, this is going to involve probably one of the most basic properties of the real numbers. Now, we all know that the real numbers are continuous, right? What that means is if I draw a line like this is the real line, then maybe this is the number 0, and this is zero point 0.9 with a bar. And let's say that this is 1. Let's say that these are distinct. Of course, we're going to show that this is actually 0 distance and that these are exactly adjacent to, I mean, they're not adjacent, they overlap, meaning they're the same point. Of course, we're going to show that. That's what this video is for. But let's just take for a moment that this is how it is. Now, forget about this 0.9 and this 1 and all of that, right? Let's ignore this for the moment. And let's just say that if I just took two numbers, 0 and some number x, then no matter how close x is to 0, right, there is always going to be some numbers in between in this region right here that I'm trying to scribble over, right? And a simple example is going to be x over 2, right? And then x over 4, uh, you know, 3x by 4, and so on. You have all of these numbers that would lie in between, right? So likewise, instead of maybe 0, suppose I had any two numbers, a and b, we would have infinitely many numbers in between. And in fact, well, we would have at least one number in between. That's a given. If we have infinitely many, then of course we have at least one. And this number could just be a plus b by 2. There could be another number, the average of a and a plus b by 2. There would be another number, the average of a plus b by 2 and b, and so on. So you would have all of these different numbers in there, right? So we can frame this symbolically, and we can say that if a and b are distinct, right? So obviously a does not equal b. That's the only reason why there is some space between them, right? So if a does not equal b, then there exists an element p, okay, where p is a real number, right? So take p is a real number, right? That's the domain of quantification. We want to be correct with our quantifiers, such that a less than p less than b. All right. So this is what we're going to do. Now, there's a certain property of statements of this form. So this is nothing but an if this guy, then this guy. That's how you read statements involving this. And I'll maybe do a video on this later on in my logic series to explain this more rigorously. And this guy is called a quantifier. It's an existential quantifier. It just means there exists. Yes, there is at least one. So anyway, statements of this form, if and then statements, have the property that their contrapositive is also true if they are true. So what is a contrapositive? Well, I'm not going to talk about that now. I'm going to assume that you're familiar with the topic. If not, do check out my video on the subject. You should be able to see it above, and I've also linked it in the description. Right? So anyway, so we apply contraposition by negating this guy, right? By negating this guy, and then saying that the negation of this guy implies the negation of this guy. All right, so that's what we're going to do, and let's just go ahead and negate those statements, giving us if there is no p such that like a less than p less than b, then a equals b, right? So we know that this first statement here is true, like I just showed why this is true. So if that's true, then it follows that this statement also must necessarily be true. In other words, if we want to prove that two real numbers, and this is specific to the real numbers, remember, if there are two real numbers, if we want to prove the equality of two real numbers, it is sufficient for us to prove that there are no real numbers between them. So to prove the equality of two reals, it suffices to prove that there are no reals between them. So the reason why I'm writing this out over here is just so that it all becomes very clear what we're doing and why we're doing it. All right. So now, all right. How do we prove that there are no integers? So first, pardon me, real numbers. So the first thing that we're going to do is we're going to take a is equal to 0.9 with a bar. I'll just use that for short, and b equals 1. And we're going to try and prove the equality of these two. So we're going to do that by proving there are no real numbers between them. So how do we prove that there are no real numbers between them? Well, if there exists some p such that 0.9 bar less than p less than b less than 1, I can just write 1, then we have p is equal to 0.9 bar plus q, where q is a real number, right? So it's pretty obvious. Any real number can be expressed as the sum of two reals. The real numbers are closed under addition. We know this for a fact. And if you don't have any clue what I just said, what I mean is that um, sum of any two real numbers will also be a real number. So it's anyway. So p is greater than zero point 0.9 bar, right? By this definition here. So it automatically follows that q is going to be a non-negative number. And in fact, what we're going to prove is we're going to prove that q is equal to 0. Because if q is equal to 0, then any p would have to equal zero point 0.9 with the bar itself, meaning that it falls out of this interval 0.9 bar comma 1, where this means all the real numbers between 0.9 bar and 1, not including it, right? So if p is equal to 0.9 bar, then it's excluded from this range, right? So let's understand why q is equal to 0. So let's just write out 0.999. I'll just throw in a couple of dots. I'll write another 9, and I'll throw some more dots in there. Right, so there are infinitely many 9s. This is, it's fairly easy to see this. And let me say plus q. So q, I'm going to put several values. I'm going to explain what the value of q is over here. And over here, well, this looks somewhat like addition, but it isn't quite. I mean, you'll see what I'm going to do here, right? So here, I'm going to say, is this less than 1, right? Because the premise is that p must be less than 1. So we're going to say that if q is anything other than 0, then p will exceed 1, which means that q will have to be 0, which means that p will not be greater than zero point 0.9 with a bar. So that's really how we're going to approach this. Now, q. So q can only contain digits from 0 to 9, right? It could only be 0, 1, 2, 3, 4, 5, 6, 7, 8, or 9. Those are the only possible digits that q can consist of. It can have as many decimal places as we want, whatever. We're dealing with base 10 numbers, right? So if we wanted to do that, what would the minimum number be that we could have over here? Well, if we had a 1 over here, then we would get the answer as, 1.999, etc., which is not less than 1. So this statement is going to be false, right? Because the sum is not going to be less than 1, it's going to be greater than 1. So what that means is that this is not 1, this must be a 0. Right, so what could we have over here? Well, of all, why did I take 1 first of all? It's because of the digits 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Well, we don't want to start off and say that it's a 0. So the next smallest is going to be a 1, right? So we start with a 0. So let's try and put a 1 over here because that's the smallest of the digits 1 to 9. So again, if this were the case, the sum would be 1.09999, etc. Right? So again, the resulting sum would be greater than 1. And we don't want that. So again, we would have to make this guy equal to 0. So what if this guy equals 1? If this guy equals 1, again, the sum is going to be greater. It's going to be 1.00 and then 99999, whatever. So that's still going to be greater than 1. 1 followed by 0.0000. And even if I have a 1 somewhere at the 100th decimal place or something, that's still going to be a number greater than 1, right? It's still going to be a real number bigger than 1. So we can't have that. So again, this is a 0. This is a 1. No, this can't be a 1 because then this is again a 0. This is again greater than 1, so this is a 0. And you can see how this argument continues. So even over here, if at all we were to put a 1, this condition would be violated, meaning that, this has to instead be a 0, and so on. In other words, Q is equal to 0, right? Why is Q equal to 0? If not, right, we have P is greater than 1. Q is not less than 0, right? Q is not a negative number because if so, P is less than 0.9 with a bar, which again, we don't want. So can Q, be, so what I mean when I say if not is, if Q greater than 0, that's really what I mean. So when we have Q equals 0, we have P equals 0.9 with a bar. But what this means is that there exists no P such that 0.9 with a bar is strictly less than P less than 1. This is strictly less. This is not a less than or equal to. Oops, I was about to underline that. Then I realized that would be less than or equal to sign. But you know what I mean. This existential quantifier stands satisfied, right? This means that there does not exist, which means this statement as a whole is true. And we know that this implies that 0.9 with a bar equals 1. Quod erat demonstrandum. Thus it is proven. All right, so I hope you all found this a satisfactory explanation of why 0.9 with a bar equals 1. Just to summarize what we did, we showed that 0.9 with a bar and 1 cannot be separated by any real numbers. In other words, there are no real numbers between the two, which means that they would have to be exactly the same. Those of you who would like to think about this in terms of intervals on the real number line, maybe if you have some ideas regarding how you could look at this with regards to the greatest lower bounds and the least upper bounds of certain intervals, perhaps the interval 0.9 with a bar 1, the open interval I might add, that's a very interesting way to look at it. Do comment your views and I would love to go through them. If you want to present the algebraic, the very straightforward approach that essentially shows that maybe 1 over 3 is 0.333 and 3 over 3 is therefore 0.999, but 3 over 3 is 1, something like that. By all means, go ahead, share that with me. I just wanted to present this particular approach. The reason being, I believe it really underscores the power of the power of the real number line, essentially. If any two real numbers are distinct, then you would have infinitely many and definitely at least one real number separating them. So that's the power of the reals. If you want to explore more about reals and real analysis, I recommend that you do Stanford's Introduction to Mathematical Thinking online course. Now, the course itself is largely about about logic and about how to approach mathematics in general. But there is one module where Dr. Keith Devlin of Stanford approaches real analysis using these insights. Yeah, Introduction to Mathematical Thinking. It's available for free on Coursera, and I have linked it in the description. Do check it out. I hugely recommend it. Well, that's it from me for today. Thanks for watching this quickie on the fundamental theorem. Do like, subscribe, and I hope you had a great time learning about the real numbers. Thank you. See you next time.